Welcome to our lecture on metric spaces. Today, we are going to explore a foundational concept known as neighborhoods. If you have ever wondered how mathematicians rigorously define being close to a point without relying on exact distances, this is where it all begins. Understanding this will unlock advanced calculus and topology. Let us dive in. Before we look at the math, let us build some intuition. Imagine you are standing in a crowded room. Your personal space is a small, invisible bubble around you. If we draw a large, weirdly shaped chalk outline on the floor that completely encloses you and your personal space bubble, that outline is your neighborhood. In mathematics, it does not matter how jagged or strange the outer boundary of a set is. The only strict requirement is that you can inflate at least a tiny, perfect mathematical bubble around your point, and that entire bubble stays completely inside the set. Now that we understand the bubble analogy, let us translate it into the formal language of metric spaces. A metric space is simply a collection of points where we have a specific rule to measure the distance between any two points. Suppose we have a metric space X and a specific point X living inside it. We also have a subset of this space, which we will call N. We say that the set N is a neighborhood of the point X if we can find a positive radius such that an open ball of that radius centered at X fits entirely inside N. This brings us to the mathematical condition for a neighborhood. The formula states that the open ball B centered at X with radius epsilon must be a subset of N. Conceptually, this means our perfect bubble must live entirely inside the set. The symbol epsilon represents a strictly positive radius, no matter how microscopic. The subset symbol means is completely contained within. If you shrink epsilon to be very small and the ball still spills out of N, then N is not a neighborhood of X. Let us see this visually. The diagram on your screen captures the essence of our formula. The irregular amoeba shape represents our set N. Notice that N does not have to be a circle itself. It just has to be large enough to contain one. Because it successfully swallows the entire dashed open ball centered at X, it qualifies as a neighborhood of X. The point is buried safely inside the set, away from the edges. Before we move on, let us see this with a concrete example. We will use the real number line with the standard distance metric. Let our set N be the closed interval from 0 to 5. We want to determine if this set is a neighborhood of the number 2. To prove this, we must find at least one positive radius epsilon. This radius will define an open ball centered at 2, which on the real number line is simply an open interval. Continuing with our example, we set up the mathematical formula for an open ball on the real number line. We take our center point, 2, and stretch out by a distance epsilon in both directions. We have the freedom to choose any strictly positive value for the radius. We do not need the largest possible radius, just one that works. Let us pick a simple radius of 1. By plugging this in, our open ball becomes the open interval from 1 to 3. Now we compare our test bubble to our original set. Every single number strictly between 1 and 3 is clearly also between 0 and 5. Therefore, our open ball is completely contained within the set. Because we successfully fit a bubble around the point 2, we have proven that the closed interval is indeed a neighborhood of 2. The point is safely inside the buffer zone. Now that we have seen a successful case, let us explore a different scenario using the exact same set. Our set is still the closed interval from 0 to 5. However, this time we want to test a point that sits right on the edge, the number 0. We need to test if it is possible to draw an open ball around 0 that stays entirely inside our set. We set up the general formula for an open ball centered at 0, which stretches from negative epsilon to positive epsilon. Let us see what happens for any arbitrary positive radius epsilon. Because the radius is strictly greater than 0, any negative fraction of it is a negative number. For instance, negative epsilon divided by 2 is a specific negative number that lives inside our open ball. This proves that no matter how microscopic we make the radius, a perfectly symmetrical bubble around 0 will always contain some negative numbers. Now we look back at our original set, which only goes from 0 to 5. This set does not contain any negative numbers whatsoever. Therefore, the negative numbers we just found in our open ball cannot possibly be in our set. The negative half of our open ball has completely spilled outside the boundary. It is physically impossible to fit a protective bubble around 0 that stays inside the set. Thus, we conclude that the closed interval is not a neighborhood of the point 0. This brings us to an important question. Why do we care about neighborhoods in advanced mathematics? In calculus and physics, neighborhoods form the absolute foundation of local behavior. When we study concepts like continuity, derivatives, or limits, we do not care about what a function does a million miles away. We only care about what happens in the immediate, microscopic vicinity of a specific point. In real-world engineering, a neighborhood represents a safe margin of error or a tolerance zone for manufacturing parts. Let us summarize what we have learned today. A neighborhood of a point is any set that acts as a protective buffer zone, ensuring the point is safely inside and not teetering on the absolute edge. The strict mathematical requirement is that the set must have enough room to swallow at least one tiny, perfect open ball around the point. While the open ball itself is perfectly symmetrical, the neighborhood can be any irregular shape at all. You have now mastered the foundational concept of neighborhoods in metric spaces.